Okay, we're going to have a look at some differentiation. For further maths, we need you to have a look at some of the year 13 normal maths, and we need you to have a look at differentiation of sin and cos before you can carry on with the further maths stuff in year 13. Anywho, let's just have a look at what happens when you differentiate sin x, and we'll just sort of do it sort of fairly intuitively. We like trig functions, by the way, because they're a bit like polynomials. You know, they're very sort of easy to manage, and you can do things with them. That looks about 1. Here, the gradient's about 0. Here, it's a bit like that one, except it's going down the slope. 0 again, and then it looks like we're coming back up to 1 again. It shouldn't be too much of a shock to us that it turns out that the result if y equals sin x, then dy by dx is equal to cos x. And if you forget that, just quickly sketch it out and, oh yeah, it makes sense. Let's do the same sort of thing with cos x and see if we can differentiate that. Well, it starts off at 0 to begin with. It's negative, we know that, and it's actually at 45 degrees, it's minus 1. Comes off at 0 again, 1 there at that point, and then back to 0 at the end, just sort of working through some key points within that graph. And it's not a surprise to us that dy by dx actually it's not quite sin x, it's a reflection in the x-axis minus sin x. So there's our results, basic results of differentiating sin and cos. We can go a little bit further with these definitions and actual sort of standard results. If y is equal to sin x kx, let's say, we'll put a number in. It turns out, just accept it at this stage please, that dy by dx is equal to k cos kx is what you've got. Similarly, for y equals cos kx, it turns out the result is dy by dx is equal to minus k sine kx. It's just an extra little bit so you can start dealing with more complex things. So if you had something like, let's just make something up, y equals 3 sine 4x plus, let's go for cos 2x. We could differentiate all of that thing fairly quickly actually. Dy by dx would be equal to, the sin is cos, so it's just cos 4x, and we do have the 3 there, but we also have a 4 in as well, so it's 3 times 4, which is 12. The cos becomes a minus sin 2x, but we also have to times it by 2 as well, so we'd have something like that. So we certainly want you to get really quite comfortable with accepting these results to start off with, but just applying them by doing this level of differentiation at this stage. Now then, if that's all you can sort of, if you want to just leave it at that for the time being, that's fine. Have a go at the exercise, which I'm going to show you in a minute. However, you are expected to go a bit further and give more rigorous proof of those results. And that's where things get technical. However, it also gets very interesting. You're going to have to slow down here a little bit when you start looking at this stuff. I've got an extract from the, what do you call it, formula booklet, and there is a couple of things that we look at. Look at this bit of trigonometry, which is really brilliant. It's called the compound angle formula, which you will be looking at fairly soon or have already seen. And we've got those two, which are really useful. Very nice that they're in the book, and we can start getting other bits out. And we want you to be able to get other bits out. I'm just going to give you an example of being able to work with those formulas. Let's have a look at cos A plus B, and we'll look at, I'll just get the formula first of all. It says cos of A plus B. Just notice that they've saved ink here. There's actually 2 formulas here. It says plus minus, and then it says minus plus. In other words, if this says plus, it says minus here, and if it says minus, it's plus here. So we've got cos A cos B, cos A cos B, and then it says minus. You switch the signs around, sine A, sine B. Okie doke. We don't switch the signs around in that one, and it's going to be really useful in both bits of maths, further maths and your normal maths, to be able to do quite simple sort of work on getting other bits and bobs out. So suppose A was equal to theta and B was equal to theta. Could you simplify that? I'd stop the video and have a go. We get cos theta minus sin theta, which of course is equal to cos squared theta minus sine squared theta. That, of course, theta plus theta is 2 theta. So that result is very, very nice. Just kind of compare this with cos squared theta plus sine squared theta is equal to 1. Of equal status is this identity, cos squared theta minus sine squared theta is cos 2 theta. So the cos 2 theta formula is very important. And in fact, there's a couple of different versions of it, because you know you've got a nice little identity, which is 1 minus sine squared theta is how you can write that. 1 minus sine squared theta minus sine squared theta is another way of writing it. In other words, 1 minus 2 sine squared theta would be another way of saying cos 2 theta. When you're looking at this formula, just to sort of put it in words here, don't worry about this theta here. It's just describing what this theta is. This theta is half of whatever that is. That's all that's saying. So if you wanted to, if that said theta, that would have to be 1 equal to 1 minus 2 sin squared of half of theta. So you'd have something like that. So that's quite a nice result to have a little look at. So we certainly want to start looking at things like the compound angle formula when we're doing some harder questions about trying to prove why cos theta differentiated is minus sine squared theta, for example. So that could be a useful little tool for us down the line. I'm just going to park that over to one side and we'll have a look at something else, and that is the idea of radians. Degrees are useless. It's just historical that we have 360, and you know now, very importantly, that actually a much more useful definition of a unit of angle is actually quite a big angle is 1. This 1 degree being a little thing, that's 1 radian, that's just of unit 1. And how is it described? Well, it's described as that. It's defined rather as being that. 1 radian is the angle you turn through, so one of them will give you this length is also the same as that. So that's really useful. Your maths becomes very, very easy then from then on. So if this was 5 centimeters and this was 1 radian, then you can work out that arc length very, very simply. It's just 5 centimeters. That's what the definition of 1 radian is. And in fact, it's not too difficult just to get a definition of any angle. When you're seeing that theta in radians, remember, so you've just got this as this arc length here is just r theta. Okay, so it's important that you're kind of really comfortable with arc length is just r theta when theta is in radians. The point is, whenever we do any work on integration or differentiation of trig functions, we must be in radians. Degrees is not going to work for us, but this is much nicer. The other circle that we really, really like is this circle. It might seem a bit silly, but it's important to us. It's the unit circle. And that's very important, because if you're measuring your angles in radians, which we are doing now for all our trig in calculus, integration and differentiation, we will want to be in radians. What is this length here? It's just theta. Now remember, this is about 1, so if that's 1, that's about 1. You know, it's that sort of thing. So you've got to completely forget about degrees, but you do start to get some nice results when you start looking at this. And one of them, which is very, very important, and the whole reason actually why we define radians in the first place, is what happens when your angle is small. So I'm just going to draw it like this. You've got a unit triangle. If this is theta, and I've got to set my calculator to radians, sine theta is just this length here of this triangle. If this is a unit hypotenuse, that's sine theta. But we also know that this arc length, that little arc length there, is theta. All right, so you can see, can't you, that when theta starts to get really small, this line that's dropped down, which is sine theta, gets very close to the actual arc length theta. In other words, we have this great result that says sine theta is approximately theta when theta is small. Now, you don't even need to remember that, because in here it says small angle approximations, sine theta is equal to theta. So that's why that's happening. However, what we do want to pick up on is this thing, where theta is measured in radians. All right, so any kind of calculus that we do, differentiation, integration with trig functions, we must be in radians, please. You have got another result. Let's just pick up, you know what we're saying about this brilliant sort of double angle formula, that we've got that cos theta is equal to 1 minus 2 sin squared theta over 2. I've got this result here which is useful as well, and it's straight from that compound angle formula. A little bit of playing around with it. Let's take our time over it for a minute. This notation, I'm not massively keen on it really, because it's sort of it's a bit confusing for us. Well, it's confusing for me. So it's 1 minus 2 sin theta over 2, and it just means that that entire thing is the thing that gets squared, and that's probably fine for you, but I like that because it's really clear what that means. It's just a bit of shorthand. There's nothing mathematical about it. It's just I can't be bothered to write it, but that actually you can see what's going on. Imagine when theta is small. This sine theta over 2 just becomes the same as theta over 2. So this becomes 1 minus 2 times by theta over 2 all squared, because we know that sine theta gets very close to theta when theta is small, and that leaves you with equaling 1 minus theta squared over 2. You get that. That's what cos theta will be when theta is small. And again, you don't need to remember, you don't need to prove that necessarily, but it's good to be able to. Of course, we want you to be able to kind of think through it. You can see it there. Cos theta must be equal to 1 minus theta squared over 2. Where does that come from? Well, it comes from this result here, compound angle formula, when we get the cos 2 theta from there, and also the result that sine theta is approximately equal to theta. So that's what those bits are there for. This is going to be very, very useful when it comes to you proving results from first principles, which is this thing here. It gives you the formula for proving differentiation from first principles, which you actually looked at in year 12. I'm going to go through one. I won't spend a huge amount of time on it, but it would look something like this. You wouldn't necessarily draw the graph, but I'm just going to draw the graph of sine just to sort of get into it a little bit. And it's useful at first just to think about working out the gradient of a chord, and this would be x and that would be x plus h. So you look at those different points and you work out the change in y and the change in x. The idea is as h becomes really small, so small in fact that you get the gradient of the tangent at this point. So I'm going to use the formula that we are given here. It says, and I just copy it all out, so I've got the limit as h tends to 0 of f of x plus h. Our f of x in this case is sine of x plus h, carrying on with the formula, minus sine of x, and that's all over h. So that first bit I've got straight from the formula booklet. Okay, and then I can start doing a few bits and pieces with it. This is not very nice, these angles being like that. However, just going back to that trigonometry, you have got sine a plus b. You've got a formula there, sine a cos b, plus, it's the same, plus minus, cos a sine b. So I can apply that formula to this little part of it here. So that would be equal to sine x cos h plus cos x sine h. And where did I get that from? It's straight from this formula here. I would print this formula page off and then just have a look at that little line. That's where that bit's come from. And then I want the minus sine x, and that's all over h. I do just need to put in that the gradient is equal to the limit as h tends to 0. So as h gets small, we've got this. Now then, there's a bit of sort of self-steering here, if you like, because it's kind of driving itself a little bit, this what to do, because when you need to do a bit of factorizing, but you can't do any other than get the sin x's together. So this bit would be, let's just slow down a bit. We want you to slow down and do technical stuff like this. It's not that it's difficult, it's just you've just got to take your time. Sin x cos h, I'm just going to have that minus sin x over there, plus cos x sin h. You have to be really patient, and it's not hard, it's not conceptually hard at all. It is just a lot to write down each time, but I want those x's together because I want to try to factorize, and I will do. I'll take a factor of sin x out. That gives me cos h minus 1 plus cos x sin h, and that's all over h. I may as well, now I've split them up into 2 bits, do that. By the way, this kind of technical work is also seen in other bits and pieces with your differentiation and later on when you do other things. So it is useful to be able to handle this kind of work, actually. Now then, it may be that what you decide to do is just to sort of have a look at this part here and just put some values in your calculator. You don't need too much of a proof here, but you probably know that cos of 0 is 1, so when h is close to 0, cos of a very small number is very close to 1, and so you've got 1 minus 1, so this becomes very close to 0. This entire thing actually starts to just disappear. So it's equal to, this part's actually 0. The other thing that we've got is sin h over h. Well, you know that sin h becomes very similar to h, becomes as close as we like to h. And in actual fact, as h becomes very small, sin h over h gets as close as we like to 1. In other words, this whole thing gets as close as we like to cos x. And it would be absolutely fine in the exam to go from this stage to that stage just to do that. I would be tempted, just to sort of, by the way, this is in the book, it's one of the sort of examples. I would be tempted just to kind of learn it and rehearse it a few times and just, are you comfortable with it? And you gain a lot from that, actually, because you get good at coping with lots of detail. You might sort of think, oh no, I can't do this. Yeah, you can. It's absolutely fine. It's just sort of a little bit, there's just a little bit of detail to work through. So that's enough, really, about that. Stuff on sin x is basically cos x and vice versa, roughly. And so you can start to have a look at a few questions and get more familiar with it. But it's important that we start pulling together bits of differentiation and integration and also bits of trigonometry in preparation for your further maths next year. I'll just show you what bits you need from the book. Okay, we'll see what we've got in the book. It's the Year 2 book, and we're just having a look at a little bit of differentiation. By the way, you'll see the word calculus being used just to mean both differentiation and integration, and it's this first bit looking at sin x and cos x, which is on page 232. So it's an interesting one, this, really, because actually differentiating is sin x and cos x is very straightforward, but we ought to at some stage have a look at some of these sort of technical issues which are not as straightforward. Just tune into these. Both of these approximations are in the formula booklet, and of course it only makes sense if we're in radians. And there is a result here that sin x over x is going to be equal to 1 for very small x, or rather we can get as close as we like to 1. We can find an h small enough so we can get as close as we like to to 1. Same with with cos. That's quite nice, that little bit there that they're putting in. They're using that approximation, and they're showing also that this whole thing here is equal to 0. I think that's well worth having a look at. Okie doke, let's have a look at some other bits and bobs. You will always need to be use radians when differentiating trig functions. When it comes to other questions on trigonometry in year 13, like using compound angle formula, and you're not differentiating, for instance, then degrees will be okay. And you'll see from the question whether they want you to do it in degrees or radians. Some interesting proof there, worth you having a look at that example, why that's true using limits. So I think that's well worth having a look at that example and working through that. Don't worry too much if at this stage this is too technical and a bit confusing, because the main thing for all of us is that we know these standard results. Y is sine kx, then differentiated is k cos kx, and then the version as well for differentiating cosx. So that's the thing that we're really wanting to make sure that we're really comfortable with at this stage. Let's have a look at some other bits. So we've got some examples. So you'd probably be able to, just do these things in your head, to be honest. This is a nice one. Look at this one. This would be cosx goes to minus sine. So this would be, minus 3 sine x. This one is cosx, but you've got 4 times 2, 8 cos 4x, etc. for that one. So the actual differentiation part of it is fairly straightforward, actually. What I like about this exercise is you've done quite a bit on differentiation and why the purpose of it, and you can find stationary points, etc. And we can do the same thing here. So this is just gaining a bit of confidence, and now you can differentiate all the stuff that you've done before on differentiation. You can do it with cos and sin as well. So all of that stuff on stationary points, that just feel confident about doing it in the same way that you did before. Now you can differentiate something. So well worth reading through that particular example. Again, this warning coming up: whenever you're using calculus, you must work in radians. Otherwise, it's just not. It's not going to work. It hinges on that fact. Exercise 9a. Then it starts off quite technical. You might struggle with that a little bit. Prove that if f of x is cos x, show that that's true. Differentiated. You get that, hence prove that f of x is minus sine x. I would have a look at the example of differentiating sine x and see if you can get it sorted from there. And then after that, use the definition of the derivative and the addition formula. That's in the formula booklet, remember. Cos A plus B is in your formula booklet, that very nice result. Cos A, cos B minus sine A, sine B is in your formula booklet. So worth just digging that out and having a look. Question 2, straightforward. Just very straightforward, using the standard result. So it would be good to start having a little bit of a go with those questions. All right, if you can sort of get up to question 5, say, that would be really, really good. And keep going. Just keep going through that exercise. Do as much of it as you can. Okay, let's stop there.